Hello everyone, this is Hadrien Hendrikx, and today I'll present you our work, Statistical Preconditioning for Distributed Optimization. This is joint work with Ling Chao and Sébastien Bubeck from Microsoft Research, and Francis Bach and Laurent Massoulié, who are my PhD advisors at Inria Paris. So in this presentation, we'll consider a distributed empirical risk minimization problem of the following form. So the objective capital F can be written as an average of local objectives fj, where fj is the local function of node j, and you can think of it, for instance, as the loss function on the local dataset of node j. So this arises, for instance, when the dataset is too big to be held on only one machine, which happens a lot in online advertising or for image datasets, which have just huge datasets. And this is also the case when the data is inherently distributed and should not be moved. For instance, think of medical data held by hospitals, or just because in general it's quite expensive to move or shuffle data around. So we adopt a centralized communication model. So in this model, we have a server that has the parameter xk. And then the server broadcasts xk to all the workers. The workers, they locally compute their local gradients, gradient fi of xk, and then they send it back to the server. The server aggregates all the local gradients, uses them to compute the full gradient, and then updates the parameter xk with this. So this is a standard parallel gradient descent, and each iteration requires back and forth communication between the server and all workers. So we'll take the following high-level approach. Our goal is to design a first-order centralized algorithm with a low communication complexity. So we want it to be as few communication rounds as possible. In order to achieve this, we'll assume that the server locally holds a function fn, which approximates the global objective in some sense that we'll see later. And the idea is to use this local function fn to change the iterations compared to gradient descent, and thus reduce the iteration complexity. And how we'll do this is using mirror descent with an appropriate Bregman divergence. So our presentation will go as follows. We'll first use the framework of relative smoothness and strong convexity to formalize this notion of how well Fn approximates F, and show that this is captured by a new quantity, the relative condition number kappa f of phi. Then we'll use concentration inequalities to give sharp bounds on kappa f of phi, depending on the size of the server's datasets. And finally, we'll briefly discuss an accelerated learning method. So the gradient descent iterations, as you have seen, can be written in the following way. So xt plus 1 is obtained by xt minus step size times the gradient. This can be written in an alternative form, and so it's a minimization problem in which we wish to minimize the dot product between our new parameter and the gradients, under the condition that the new parameter isn't too far from the current point xt. So we penalize this problem by Euclidean distance term. But actually, we could use other kind of distances, so not necessarily Euclidean. And if you plug in a Bregman divergence term here, then you obtain mirror descents. And the Bregman divergence relative to f to phi between x and xt is given by the following equation. And the important thing is, for instance, that when phi is the squared norm, then this reduces to gradient descent because the Bregman divergence reduces to the Euclidean distance. So what are the convergence properties of mirror descents? Well, if capital F is sigma f of phi strongly convex and L f of phi smooth, relatively to function phi. And so this relative regularity is just that the Hessian of capital F is lower bounded by sigma times the Hessian of phi, and upper bounded by L times the Hessian of phi. So instead of having your Hessian, which is lower bounded and upper bounded just by the identity, it's by another matrix, and the hash another function. And so in this case, the mirror descent converges in kappa f over phi log 1 over epsilon iterations to minimize capital F up to precision epsilon, where kappa is this relative condition number, so relative smoothness divided by relative strong convexity. So compared to gradient descent, what's interesting is that the kappa f in the bound is replaced by a kappa f of phi. And this is interesting because kappa f of phi can be much smaller. So now the main question that we ask ourselves is what's the best phi for a distributed use case, and what's the corresponding relative condition number? And the second question is how to accelerate this to obtain square root kappa f of phi dependence. While following the Dane algorithm introduced by Shamir et al., we choose the function phi as fn, so the local objective of the server, plus a small quadratic term. In the quadratic case, we show that the relative condition number can actually be of order the usual condition number divided by n, where n is the size of the server's dataset. So this is huge because it means that even if you have a rather small local dataset at the server, then you can already achieve very good speed up, and this just scales very well in the sample size at your server. In the case of generalized linear models, such as logistic regression, it's much harder because you don't concentrate matrices, you need uniform concentration of hashes. Yet you can still obtain that the relative condition number is of order kappa f over square root n, which is improvable to kappa f over n in some cases. So in some cases you recover actually the convergence guarantees from the quadratic case. What's important here is that our bounds improve existing ones by a square root n factor, as in the quadratic case, and they hold outside of the pure quadratic case. And we show that the quadratic performance can actually be recovered in some, but a quite large number of cases. So now I'll just skip over the details of acceleration because I don't have time in this presentation, and just present you quickly some experiments. So these experiments were done on the KDD 2010 datasets, which has 8 million samples in dimension 20 million. We chose the logistic regression objective with a very small regularization parameter of 10 to the minus 7. And we compare 3 algorithms. So Dane, which is basically mirror descent, with phi chosen as I showed you. SPAG, which is our accelerated version of Dane. And heavy ball Dane, which is, so SPAG is in dashed lines, and heavy ball Dane in the dotted line, which is another acceleration of Dane. And so we benchmark this algorithm with three different sizes for the local datasets. In orange, you have 1,000 samples locally at the server. In blue, you have 10,000 samples, and in red, you have 100,000 samples. So even though 100,000 samples looks big, it's just 1% of the total dataset. So this really isn't much. And in this case, you see that you can converge in roughly 15 iteration to very, very high precisions with accelerated mirror descent, regardless of the method. I mean, we're slightly faster, but it's not that fast. But really, the key thing is that when you have a huge local dataset, then you go fast. And then even when the local dataset isn't so big, so for example, for the blue curve, you have only you have a very small local dataset of 10 to the 4, so it's 1,000 times smaller than the big dataset, and yet, thanks to acceleration, we achieve very fast convergence to the optimum, and in particular, much faster convergence than without the statistical preconditioning. And we see that when you have only 1,000 samples, then you still achieve good performances, but of course the algorithm becomes kind of slow. So our contributions are the following. We presented a principled convergence theory based on mirror descent. We show improved balance on the relative condition number, and we have a theory for asymptotic acceleration, but we showed that it's actually quite effective in practice. So there are some open questions. One is the tightness of the concentration results, and the other one is whether it's possible to prove non-asymptotic acceleration in some specific settings, because it's actually impossible to prove it in general. There's a negative result. So I'm looking forward to hearing questions. Thank you for listening.